So we will finish debugging today, organizing and debugging MATLAB programs. I posted this as lecture 4.1. And just the basic recap is that it's important to use a good, consistent style in writing your programs. It's important to actually document them well. So here in Prolog, you would typically say what your function is doing. And then when you're writing any function, you will typically process any input data, read it in, transform it in some other format or whatever it is that your task is requiring. You will do some main computational task, and then you will prepare outputs to go out of this function. Also, it is important to kind of lay things out in a way that you can read easily and basically eyeball what's going on in the program. So these two pieces of code are executing just the same. As far as computer is concerned, they're just the same. Computer couldn't care less. But you, if you're actually looking for anything that is going wrong in this code, if it's not executing properly, then the one on the left is much easier to read and actually spot any issues. For instance, if you typed in M here instead of N and the other way around, it would be easier to spot this problem. Okay. Also, you want to actually name things in a way that has some connection to whatever physical problem you're trying to solve. Okay. So typically, you're solving a physical problem. Your variables are better off to actually have names such as thick or thickness or radius or so forth, rather than ABC, A1, B1, C1, and you at some point you run out of the alphabet and you have trouble remembering what it is that you meant by C1 as opposed to some actually slightly meaningful name. Now here you might want to optimize between the length of the name, because you have to constantly type it in as you're programming, and the actual, so instead of thickness you might want to go with thick and things like those. So that balance is on you. Okay? And you want to actually provide documentation. So here's an example documentation at the very beginning of the function. This part will print if you say help and name of the function, so in this case H2O density, then this entire preamble will print out to the screen so you can easily see how to use the function. However, you can use this notation here. Whatever you put after % will be treated as a comment, so as you read the code, it's good to put a lot of comments. And finally, there are some tools. You always have to, so we were fixing this function last time in class, and you saw that you could fix it in a different ways or put different warning statements depending on what it is that you intend to do. So what is the level of warning statements that you're going to implement in your code is up to you. So this function as written on the left really works only for scalars or maybe matrices that match. So you might want to actually have some checks in here that are checking whether those conditions are met and whether it executes properly. Otherwise, you're leaving to MATLAB to give you a warning. So for instance, if you actually have these two as just arrays or vectors of the same size, right? This function is written will not execute. So you have to implement that. So for instance, you check the sizes are x and y, and you might want to throw in a dot here, x dot times y, for the function to execute for these vectors. And also if you have matrices, you might want to check their sizes as well. So again, you do want to basically put a number of if-else statements that check your input, whether it's in the correct format, so that the output you're actually getting something that you wrote as opposed to MATLAB figuring out what it is that you tried to say. Okay. And finally, there are certain tools. Now, the traditional tool that works in any program out there is to have a lot of print statements throughout your function. So as you're computing something, you print it out, or at least one portion of it so you can see whether it executes correctly. And you at the same time come up with a very small example that you did on your own by hand so you know what you're supposed to get. So you always, when you write a function, you have to come up with a small example that is going to be a test. And you can always just sprinkle your code with a lot of print statements to actually see whether things are working correctly. Now there are certain things that work only in MATLAB, okay, that will help you stop. So if you have an infinite loop, and I actually tried that out in class 2 or 3 classes away, basically you can try to stop the program by typing in Control-C, and that should just kill the program, okay? I actually wasn't able to kill that loop that was going on my computer in class, so I actually had to resort to killing MATLAB altogether, right? So you just go and close it. Type commands or db type work as well. db type will actually, you can actually specialize it so that every time your function executes, and your function is stored in file name, you can actually let it know which line number to stop on. Okay? There is pause. You can type in pause into your computer, so it will pause execution, or you could type in keyboard, so when you execute, when the MATLAB gets to keyboard, it's just going to give the sort of the control to you, and you're inside the function. You can print out any variables that are inside the function that you normally don't have access to because they live only inside the function. Okay? So you either have to print them inside the function, or you have to somehow get access to them. So keyboard is kind of helpful to do that. And you can also insert breakpoints. Here I actually inserted the link for you to learn to do that. I kind of expect you to simply go through this and find the way you're comfortable with as you start writing the programs. Yes?
Could you just expand on the second bullet point of your keyboard? What do you mean, like you have access to internal variables?
Yes, so if you just pause, the program is just going to pause, which helps if you are maybe having like figures that are popping up, and then you can just look at them, right? So it's going to pause temporarily, without actually giving you access to go into the function and actually do something with it.
Okay.
Right?
So if you
Keyboard actually just stops and gives you a command line, and you can now start interacting with the function.
Okay.
Literally interacting, like as in you can print variable A.
Okay.
Right? And insert your statements or whatever it is, your commands. You can insert new commands because you're given the command. Okay? So it kind of just opens it up for you to add things. Okay? And same if you can insert breakpoints, and we will actually kind of incorporate this as we go along. You can insert breakpoints and it will do the same. But you can do it on multiple portions of the. And then you can also just order some sort of a print message. This is just a kind of a more beautiful print of an error message if you'd like. Okay. Again, it depends on what you're comfortable with. The majority of people who just do things by themselves in various programs, to this day, you just print. So for instance, I have a program that has a page, and sometimes I'm looking for where does it, sometimes it has a memory error that just kills everything. So I'm going to go and say, printf Masha 1, printf Masha 2, printf Masha 3. So I'll see where I got to which Masha did I reach, so I know which segment of the program to focus on. That's a very simple way. So whatever works for you, right? Okay, you're in the control, you're the writing, the printouts and controls and stuff like that. So you're the one designing where you want to stop. Typically you have a problem in certain number of lines of the code, and you basically want to isolate those and figure out what's happening with it. Now, all of these debugging tools, they're actually there to help us find out errors that we put in inadvertently. So those are errors that technically we could avoid if we were more careful. Now, we can never plan on being absolutely careful, so that there's a certain level of debugging that we will always have to go. And now we will actually move on to the errors that are simply there, and we cannot do anything about them, we can just know about them. Okay? So there are errors that we can avoid. For those, we use debugging tools to find them out. And there are errors that we cannot avoid, and those we will actually now go through. So these are, the topic is unavoidable errors in computing. I don't think I posted this file. Is it helpful if I post it right now? It is? Okay, yes?
Will you ever ask us to debug like a sample code on an exam?
I might,
Okay. So
if I throw in a really obvious error.
So we would have to input like pause, like insert pause here.
Right. But in effect, I don't need to do that. That could be a cool question to ask on an exam, right? You will have to debug your own writing, right? So you will write something and you will have to scan it for your errors because you might throw in a mistake. So you have to actually, as is, develop an inquisitive, like, okay, is this going to work the way I intended it to work? And on exam, you don't have MATLAB to try it out. So you actually have to kind of go line by line and ask yourself, what will MATLAB execute here? And kind of try to write it down. And that way you will walk yourself through your own code and try to catch mistakes. Okay. And as in anything, practice makes perfect. Let me quickly save, print, one. What is going on here? Okay. Okay. I'm gonna post this now. I thought I did, but then I just realized now I did not. Okay. Courses. No. All right, it's up there. So it's a 4.2 errors. This was, yes. So we went through basically organizing and debugging MATLAB programs from the errors that we can remove. And today we're going to start a discussion on errors that basically we cannot avoid. We just have to know about them and try to work with that. So what are those errors? Some of the errors, they're typically called round-off errors, where I have an exact mathematical expression or exact number that might have infinite number of digits after 0. And on computer, I have finite space where I'm trying to fit in that number. And we're actually going to go over how does a computer fit in those numbers for us. Okay? And you might have already noticed that those round-offs that show up while using your calculator. Right? So those are certain things that we cannot avoid. We certainly have a finite space to fit, finite container to put something in. And we will see where our limits are. It can happen with just representation of numbers, or it can happen with then using, so let's say that even I have two numbers that I can represent really well and exactly, but actually they're far apart. So once I actually start doing arithmetic with them, I'm going to introduce an error because of this finite size of a container. That happens a lot when I'm adding a very large number, say 1,000, plus 0.000001, okay? Those two might actually have a very good representation on a computer individually, But once I start adding them, that addition doesn't have anymore, and we'll see that that will make sense in a moment when we go over the details. So in that sense, this might get simply rounded to 1,000, so I may as well skip doing this addition, right? And finally, there are certain truncation errors where I have a mathematical formula, and you've done in your calculus class infinite series, okay? And those infinite series, I cannot go to the infinity. I have to chop it off somewhere. So I will go to 10,000, 100,000, 1 million, but I will chop it off somewhere. Okay? And that creates an error. Sometimes it's an error I don't care. It's I'm good enough, and I actually have to be a judge of how much error does matter to me. And the way I'm judging is based on the problem I'm solving. So here's an example. I'm traveling to San Antonio. Okay? I know that I have to head down I-35, and I have roughly how many miles to San Antonio? Can you do a quick Google search, tell us what the mileage is? So if I'm filling up my gas tank, okay, filling up my gas for 70 miles or 71 miles is kind of the same thing, still the same tank of gas, right, that will actually get me there. And this plus minus 1 mile doesn't really matter, okay? 73 miles, so we were actually pretty close, okay? So 73 or 70 or 75, I'm going to go to the gas station and do the same thing regardless of a change of miles over there, okay? Plus I'm going to be probably driving around San Antonio a little. I'm not just going to go there and come back. So in terms of what I needed this estimate for, how much gas to buy, 71 or 72 or 73, it doesn't really matter. So this error of 1, 2, 3 compared to 70 miles doesn't really matter. Okay? So I'm actually a judge of that. How precise do I need the measurement to be? Again, distance from here to the main office, distance with steps that I need to make, millimeters doesn't matter, inches don't matter, right? Maybe I'm carrying about like 1 step, which is 1 foot. So everything down to 1 foot is a good estimate of distance between here and there. But if I actually need to really clear, I'm ordering a material, right? So I don't know, crown molding for a room, then I actually have to have precise to a millimeter, because the moment I have this much of a gap on my wall up in crown molding, I'm gonna see that, right? So in that case, it does matter to measure precisely down to a millimeter. So things depend on your application. Where it is that this error that piles up, when does it become significant? Okay. Now, again, I mentioned already that I have a fixed number of digits typically to represent the number on a computer. And the less memory I use, the faster I am. So sometimes there's a trade-off between how precise I want to be and the speed with which I'm going to process my data. Okay? So one example I can have for you is the following, and that one is from my research. I typically work with X-ray images of rocks. Okay? They're called micro-CT. So I'm getting these cubes of data. They're three-dimensional arrays of data. And often, I'm talking about resolution that is in microns. So let's say that it's 5 microns. If I have 1,000 points times 5 microns, that's a length of 5 millimeters. Okay? So I'm talking about scanning a piece of rock that is 5 millimeters by 5 millimeters by 5 millimeters. Okay? And that's 1,000 cubed. Now if I'm using, we're going to get to bytes, but you already probably know something. If I'm using 1 byte of data to represent every number that I have there, we're talking about roughly 10 to the 9 of bytes, which is 1 gigabyte of data. Okay? 1 gigabyte. Do you know what's the memory on your computers? Working memory, also known as RAM? 8 usually. Typical laptop these days is 8. Mine is 16 because I care about having more memory, right? So basically, the moment I read this 1 gigabyte of data, I have used 1/8 of the entire memory I have. Now let's assume that each number coming from a scanner, and I have 10 to the 9 of them, 1 billion of them. Okay? Let's say that it's represented with the 8 bytes, which is so-called double floating precision for numbers. Okay? Then I'm actually using 8 gigabytes just to store that. Okay? So I cannot actually, the moment I read those 8 gigabytes of data into my memory, I'm done. I have no more memory left. Okay? So I cannot go then do something with that data, because the moment I do something, I'm computing something else, and that something else is extra 8 gigabytes of data. Okay? So you will quickly, especially in petroleum engineering, run out of memory. Okay? And data these days is everywhere. We're in the world of big data. You might have heard that big data word. There's data streamed from offshore drilling constantly. Every minute you're getting another set of data. Okay? Your pressure, your measurements along the, right? RPMs, everything is coming in. And you're storing that every minute. Well, we know how many minutes there are in days, and drilling does take more than 1 day. Thank you for asking. Okay? So we have immense amount of data that is a problem to store, and it's also a problem to read into our working memory and actually process, do something. Because ultimately we want to process data and get actual information that can help us make a decision. Okay? So it's important to actually know the differences. So basic unit is in computer, it's 0 or 1. So I can actually turn a switch on or off, okay? And on is 1, off is 0, okay? And I have 1 bit. These bits are organized into bytes. So each byte has 8 bits, okay? And that's my primary sort of unit that I'm working with. And I have just gave you an example. Sometimes I have data that is just, basically I have, my data is all in terms of 0s, 1s, 2s, 3s, 4s, maybe up to 10, okay? So 1 byte is enough to represent all my data nicely, okay? But for real numbers, I might need 4 bytes or 8 bytes to actually do a good job. So I might have these words, we're calling the word, is the smallest addressable unit of memory that actually stores some information I'm interested in. So we could use 8-bit, which is 1 byte, 16-bit, which is 2 bytes, or 32-bit, which is 3 bytes, or so forth, 4 bytes, or so forth, to store that number. Okay? And we will see how does that affect the size of numbers we can actually effectively store. So types of numbers, as we know, we have integers, 3s, and 186 minus 29. Okay? I can have real numbers, and I can have complex numbers. We were not going to, in this course, really work with complex numbers a lot. They're really a set of 2 real numbers for all intents and purposes, right? So I have the real part and imaginary part. So knowing how to store real numbers, I just need 2 sets to actually get a complex number. So we will not spend too much time on complex numbers.
Question.
Yes?
So if we're using an 8-bit system, how does a 9-digit number get stored? If we're using an 8-bit system.
Getting ahead of me, so we're going to build up to that. Okay? That's all right. So first thing is we need actually a system. So the system we work in is we have digits that are 0 to 9, right? And we go in multiples of 10s. That's how we increase. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I go to 2-digit numbers. They start with 10 to 19. 10 to 99. Then I have 3-digit numbers and so forth. This has likely ruled why. Why do we go in multiples of 10 and not multiples of 8? Why? Look at your body. Why? How many fingers do you have? 10. Okay? That's why it's easier rather than 8. If you had 8 fingers, probably we'll use that's called base 8. But we use actually base 10. Now, what does computer have? Computer doesn't have fingers. It has a switch, which is on or off. And switch has 0 or 1 digit. Okay, the moment I have 2, I'm overboard. Okay, I can do just only 0, 1. So computer actually works in what's called base 2. So it depends how much you have to count with, really. And the base itself is somewhat arbitrary. Okay, it started with 10 because humans have 10 fingers. Okay, so they do multiples of 10s. But computers can't do that. So we need to actually know something about the base. So here's an exercise. So if you have coins that have only 1 cent and 10 cents, what is the least number of coins to represent 25 cents? How many of each? 2 of 10 and then 5 of 1, right? So I'm trying to maximize the large ones, right? So I'm looking for the largest multiple of the 10-cent coin to fit into, okay? Well, that's precisely what 25 is in base 10. It's 2 times 10 plus 5 times 1. That's what it means to be represented in base 10. Okay? Now, so that's base 10. Now imagine that you have coins that are 1 cent, 2 cents, 4 cents, 8 cents, 16 cents. How would you do that?
16, 8, and 1.
So you look at the 16 you can fit. Can you do 2 times 16? No. So you can't go with 32 as a power of 2. Okay? So these are actually powers of 2. Okay? 1, 10, 100, 1,000 are powers of 10. So we look at the powers of 2. Okay? So I have 1/16. Then what's left? 25 minus 16 is 9. What's the largest one I can fit in there and how many? 8. So I have 16 plus 8 is 24. What's left? 1. So I have 1 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Do you agree? So this is my binary representation of number 25. Okay? I go in powers just like I went in powers of 10. This is 10 to the 0 is 1, right? So 5 times 1 plus 2 times 10 to the 1. Okay? Now I'm working in powers of 2. So I have 1 times 2 to the 0 plus 0 times 2 to the 1 plus 0 times 2 to the 2, which is 4, plus 1 times 2 to the 3, which is 8, plus 1 times 2 to the 4, which is 16. So this is a binary representation in base 2 of my number 25. I can do this with any base. If I had base 3, I would work with 1, 3 to the 1, 3 to the 2, which is 9, 3 to the 3, and so forth. Yes? So now let's go back to, so this is 5 digits in this base, okay? And typically I would use at least 1 byte, which is 8 bits to represent this. So I would just fill in the zeros here. So I would have 0, 0, 0, 1, 1, 0, 0, 1, and that is the representation of number 25 in 1 byte of data for computer.
So you read these from the right?
That's a great question, but yes, for all intents and purposes. Some computers do from the right, some computers do from the left. That's a hardware issue. But we're not gonna go into that, okay? So basically, we actually now represented this 25 in 2 systems. One is the decimal system base 10, that's the one we are very much used to, okay? And the other one is the binary system base 2, which is more natural for computers because they don't have 10 fingers, they only have on and off switch, okay? Electricity on, electricity off. Okay, so typically I could actually use this. So I have to first agree with myself and with the computer. So for this integer, 25, what is my size of the word going to be? How many bytes I'm going to use to store that data? And I could go with 1 byte, which is 8 bits, 16 bits, and 32 bits for integers, typically. So if I had this base 2 system, okay, and this was my representation in binary case, I would just kind of fill in. I could also look at 173 and do the pretty much same exercise, which I would then increase the powers of 2 that I would use. Okay? So 173, the largest power of 2 that fits in is 128, which is 2 to the 7. 32, 8, 4, and 1. Okay, so you can double check this. So the size of the number I can represent depends on how many powers and how many. So here I obviously have a limitation if I'm just using 1 byte of data and these 8 bits. Okay, my largest number that I can do is 2 to the 7 plus 2 to the 6 plus 2 to the, right? So put in 1s everywhere. So basically, depending on that, I'm going to choose whether I'm going to do 8-bit, 16-bit, and 32-bit. Now, so basically, if I actually decided to go with the 16 bits, okay, the largest number I could represent would have 1s everywhere for all of the powers of 2. So I would have 2 to the 15 plus 2 to the 14, all the way down to 2 to the 0, which is 1. And that number, actually, this is a mathematical formula, is 2 to the 16 minus 1. The formula I'm using here is that if you have 1 plus x plus all the way plus x to the n minus 1, that is x to the n minus 1 divided by x minus 1. So if you plug in 2, you will get that 1 plus 2 plus all the way 2 to the 15 is 2 to the 1 power more 16 minus 1 divided by 2 minus 1, which is 1. So that's 2 to the 16 minus 1. 2 to the 16 minus 1 happens to be 65,535. So if I have integers and I want to positive integers and I want to represent them with 2 bytes of data, the largest integer that I can go up to is 65,535. Is that always enough? Sometimes yes, sometimes no. Okay. So if I have this finite size container in this representation, these are the largest numbers I'm going to go with. Most often I will actually go to 32 bits because that gives me a much larger number. Okay. Now one thing that we forgot in this is a sign. Is a sign positive or negative? My number. Positive. What if I want to do negative numbers? What do I have to do? Sure. Where do I store it? If I have 16 bits, where do I store it? Right. So I'm going to reserve 1 bit for sign. But then that makes the smaller, what's left is actually my number. So that makes the range different. So it's going to be half of this, essentially. Okay? I will go from negative half of this to positive half of this, right? But I'm going to have a finite container. So basically, this is how it looks like if I have 16 bits. So basically, one of them will be reserved for the sign, and the rest of them, I think this is that 173 that we use. So this would be a negative 173. So the rest of the bits are there for magnitude. Does this make sense? Yes?
Is there a choice if we're going to put the sign or not, or do you always have to put the sign?
Well, it's a choice. So you can choose your numbers to be signed integers or unsigned integers. So by default, actually in MATLAB, by default, to avoid all of these issues, it's actually double precision floating point numbers all across, okay? Just to avoid that. But in any other programming language, you would actually, before defining a variable, we know that in MATLAB I just go in and say a is equal to 2. And the variable a is created. That variable is actually double, it's double precision, it's not an integer. Okay. But I could intentionally say, do not use doubles, use unsigned integers to do it. If I want to control the size of the memory that it stores. Yes?
How could you make a signed integer interact with an unsigned integer, given that their indexes would be different?
So basically, if I actually try adding unsigned integer to an integer that is signed, I'm going to have issues. Okay? So MATLAB or a program will have to convert it first to something that can contain both.
Is there just a function for that?
There are functions for that.
So we can
But that's
access
also,
it.
yes, so you can actually go in control of that. If you let go of control, MATLAB will do everything in double and you will avoid issues of having different. But in any other programming language, you have to be careful. Because you create garbage.
Yeah.
Okay? The way we will see floating point numbers are done completely differently. So actually, unless my computer knows what is the memory that it's accessing, is it an integer, is it a real number, it doesn't know how to read it correctly. Okay? So this matters, big time. Okay? So if I actually had a 25 here, and if let's say that we go with a 16-bit integer that I have like containers here, how would 25 look in this container? What would I have as a sign? There would be a 0 here because it's positive. 1 is for negative. Okay? So there would be a 0. And then my 25 had 1, 1, 0, 0, 1 here. So it would be 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, up to here. And the rest I would just fill with zeros. Okay, so there would be a whole lot of zeros for 25 in this type of representation. Does that make sense? So I just fill in what I don't have. Okay. Now what are the limits here? Okay. So if I had just 1 byte of data, okay, and I reserve 1 bit for a sign, and the other 7 bits I can actually fill in with 1s to have the largest number. Okay. This one here, this one corresponds to the power 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. So I have a sum of all of the powers of 2 up to the 6. Based on the formula I wrote here, that's actually equal to 2 to the 7 minus 1 divided by 2 minus 1, which is 2 to the 7 minus 1. Okay. 2 to the 7 is 128, so the largest number that I can have here is 127. Yes? Now, the range of integers that I can then represent, since I have this 1 digit reserved for a sign, is from minus 127 to 127. Are you with me still? Yeah? So what is this number in that representation? It's a negative 0. Okay? Negative or positive? 0 is actually a positive. It's a positive 0. 1 is if I put a minus in there. It's a matter of convention, so somebody has to agree on what will it be. Now, but obviously, I can have a positive and a negative 0. Obviously. So, positive and negative 0 mathematically doesn't mean much, right? So, we're wasting representations. So, one of these is actually mapped. I'm leaving 0 as a positive 0, okay? But I'm going to do negative 0 as minus 128. And that's, again, agreement. So, actual range is from minus 128 to 127. That's the range of numbers that I can have represented with 1 byte of data. If my data comes with number 456, can I use 1 byte to represent it? No. If I attempt to do it, I'm going to get garbage. Okay? I'm going to get something chopped off, something misrepresented, something not done correctly. Okay? So this is the range for 8-bit integers. I can do the same calculation for all the other type of integers. So if I have 16-bit, 32-bit, or so-called long integer, I can actually spend 8 bytes on integers. Okay? So if I had unsigned 8-bit integer, then I wouldn't paste this spot for sign, but I have to know that the numbers are only positive numbers. And then what I'm doing is I'm representing things from 0 to 255. Okay? Because 255 is 2 to the 8, which is 2 to 256 minus 1. Questions?
Yeah.
Uh-huh.
Why is it negative 128 again?
Again, I have two ways in this convention. I have two ways to represent a 0. I don't need two ways to represent a 0. So one of those I'm agreeing to set as a different number so I have a slightly wider. Okay? Computer scientists came together and they said this would be a good idea. Okay? Okay. So again, you can do 16-bit and 32-bit signed integers. And there are actually functions that can check your calculation. So there is int min and int max. And that's going to be the last bit of information that I'm going to try to shove down your throat today. So int min of integer 8, that's 8-bit integer, is minus 128. Int max is 127. Okay? And I'm right on the money. All right. I see you Monday.